Hey everyone, and welcome. Today we are going to tackle a huge topic in differential equations, how to solve systems of them. We're going to break down this really powerful technique called the eigenvalue method. And trust me, by the end of this, you'll see how one clever guess can turn a super complex calculus problem into something you can actually solve.
So, have you ever stared at an equation like this, x prime equals a times x, and just felt your brain start to short circuit? Yeah, you are not alone. It looks so abstract, right? You've got vectors, matrices, derivatives. I mean, where do you even start? Well, what if I told you there's a single key that fits this lock perfectly? That's what we're going to focus on today. We're not just going to find the answer. We're going to understand exactly why it works, step by step, until that whole intimidating problem just unlocks. Okay, so let's get on the same page. What exactly is our locked door? It's this, a system of linear differential equations all bundled up nicely in matrix form as x prime equals ax. All this really means is that the rate of change of our variables is just based on their current values, all mixed together by that matrix, A. And here it is. This is our key. We're going to make a really smart guess. We're going to bet that the solution looks something like this, a constant vector v multiplied by e to the lambda t. Now, right now, we have no idea what v or lambda are, but they are the secret sauce. Let's break this key down. It's got two really important parts. You've got the exponential, e to the lambda t. That's the engine, right? It handles all the change over time, the growth or the decay. Then you have the vector v. Think of that as the steering wheel. It's a constant vector that just points in one specific direction. So our guess is basically saying the solution just moves back and forth along one single line. All right, moment of truth. Does the key actually fit? Let's take our guess for xt and plug it straight into our original equation, x prime equals ax. This is where the magic happens. So on the left side, we need the derivative. Since v is just a constant vector, the chain rule gives us lambda times v times e to the lambda t. Simple enough. And the right side is just a times our guess. Now look closely. You see that e to the lambda t on both sides? Well, since an exponential can never ever be zero, we can just cancel it out. And just like that, click, the lock opens. All that calculus, the derivatives, the functions of time, it's all gone. We are left with this beautifully simple, purely algebraic equation. A times v equals lambda times v. Now, if this is ringing a bell from your linear algebra class, it absolutely should. This is the eigenvalue problem. Our incredible guess worked because it turned a nasty differential equation into a straightforward algebra problem. This is huge. It means if we can find the eigenvalues and eigenvectors of our matrix A, we've basically found the solutions to our system. So, what do these eigenvectors actually represent? You can think of them as these special highways or axes in our system. Along these specific directions, the behavior is super simple. It's just pure stretching or shrinking, that's it. And any other solution is just a combination of traveling along these special highways. So let's say our matrix A has two eigenvectors. That means we get two of these simple, straight-line solutions. Each one describes a flow that just moves along its own eigenaxis, either growing or decaying based on its eigenvalue. And here's the best part. Thanks to something called the principle of superposition, we can just add these simple solutions together to get the complete general solution. We just stick some constants, C1 and C2, in front to weigh them. This one formula can now describe every single possible path in the system. Okay, enough theory. Let's get our hands dirty with an actual example. Imagine we've already done the linear algebra, and we've found our eigenvalues are -1 and -4, with these corresponding eigenvectors. How do we actually build the solution? It's literally just plug and play. We take our general formula and slot everything in. The solution is C1 times the first eigenvector times e to the minus t, plus C2 times the second eigenvector times e to the minus 4t. And that's it. That's the general solution. But usually we don't want every possible solution. We want the one specific solution that starts at a particular point in space. This is what we call an initial value problem. So how do we nail down those constants, C1 and C2, to find that one unique path? So here's our mission. Let's use the solution we just built to find the one path that starts at the point 2, 3 at time t equals 0. This is all about finding the right values for C1 and C2. And the trick is super simple. Just plug in t equals 0. Why? Because e to the power of 0 is just 1. So those messy exponential terms just vanish.
This leaves us with a basic vector equation, which we can split into two easy linear equations. We solve that little system, and bam, we find C2 is 5/3 and C1 is 1/3.
And there we have it. We take those constants we just found, plug them back into our general solution, and we get the one unique function that not only solves the system, but also passes right through our starting point. We've done it! So, let's just do a quick recap. It all starts with that key guess. X equals v times e to the lambda t. That guess is what magically transforms the calculus problem into the algebraic eigenvalue problem, AV equals lambda v. From there, we build our general solution by combining all the simple eigensolutions, and finally, we use our starting conditions to pin down the exact constants. And that, in a nutshell, is the eigenvalue method. It's an absolutely fantastic tool. But it does rely on one crucial thing: being able to find enough eigenvectors to build our solution. So that leaves us with a juicy question. What happens when the matrix doesn't cooperate? What do you do when you just can't find enough eigenvectors? Well, that's a story for another time.